Chapter 7. So the first thing we're going to go through is these things called transformations. Now the word transformations is used to cover 4 different things you can do to shapes. So first transformation, or first one we're going to talk about, are translations. Now translations just move a shape left or right, or up or down, or both. And the way that we describe a translation is by 2 numbers in brackets. The number at the top will tell you whether to go left or right. The number at the bottom will tell you whether you go up or down. If the number at the top is positive, you go right. If it's negative, you go left. The bottom number is positive, you go up. Negative, you go down. So, for example, if I had minus 3, 2, okay, this tells me to go 3 squares, or to move the whole of the shape 3 squares left and then 2 squares up. So that's a transformation. All it does is move a shape across. We need to be able to describe a translation, and actually with all of these transformations that we're going to be doing, to help you work out what to do, use the corners of the shape. Look at what happens to the corners of the shape. That will help you with all of these transformations. Next one is rotations. So with rotations, we have a center of rotation. That's the bit that doesn't move, center of rotation. Now, anytime you get a part of a diagram that doesn't move, it's called invariant. So the center of rotation is invariant because it doesn't move anywhere. It stays in the same place. We also have, along with the center of rotation, we need to know what the angle of rotation is. Angle of rotation. Now this angle is normally given as maybe 90 degrees, 180 degrees, or 270. So it's like quarter turns basically. So it's either going to be a quarter turn, or a half turn, or a 3/4 turn. You won't get anything other than that. You won't get something that says rotate this by 22 degrees. It'll always be those. So we've got an angle, we've got a center of rotation. We also need to know a direction. So with a rotation, you'll be told that it's either clockwise, which means you go around that way, clockwise, or it will either go around the other way and it'll be anti-clockwise. So I've just used an abbreviation there. So that's translations, rotations. Next thing we're going to be looking at are reflections. Reflections. Now the important thing you need to know about this are the mirror lines. Where are the mirror lines? Now the way that we describe the mirror lines at higher GCSE is by using an equation. Now if the mirror line goes down like this, the equation of that mirror line will be x equals a number, and that number will be the number of the coordinate here where it crosses the x-axis. So example, if it was x equals 3, it would cross at 3. If it was x equals -2, it would cross the x-axis at -2. So those are lines which are vertical. Oops, that's not x as well, that's y. So these are vertical lines. So vertical mirror lines. Okay. If we had a mirror line that went across like this, the equation of that mirror line would be y equals a number. And that number would be the number where it crosses the axis here. And these are horizontal mirror lines. So for example, a mirror line that had the equation y equals 7 would cross the y-axis at 7. One that had a mirror line of y equals -9 would cross at -9 on the y-axis. So what about diagonal ones? Well, we've got a diagonal one like this, x, y. Now diagonal ones, they sort of go up at 45 degrees, basically like that, going through all the corners of the squares. Now these ones are just y equals x. It's always that. It's not going to be indifferent. So if we've got a diagonal going the other way, and I'll do one of those down here, I'll need a bigger axis. So x, y. So a diagonal going in the opposite direction, still going through the origin, through the center at a 45-degree angle. This one would be y equals -x. So this is the other mirror line. So you need to be able to not only recognize those mirror lines, but actually draw them. And especially when you are reflecting in these diagonal ones here, use the corners of the shape to help you, because often these reflections come out wrong. So for example, if I was trying to reflect something like this, let's say I had a shape like that, then when I reflect it, it's going to look something like this. Yeah, so make sure it doesn't end up the wrong way around. Okay, so the last type of transformation is no, we've got two more. So no, we've done rotations. With rotations, use tracing paper. I haven't sort of mentioned that, but use tracing paper to help you do rotations. The last one is enlargements. So enlargements, and with enlargements, you will have a center of enlargement, and a scale factor. Scale factor tells you how much bigger or smaller to do the shape. Now that scale factor can be a positive number, so I write positive like that, which means it will make the shape bigger. A fraction scale factor, which will make the shape smaller. And a negative scale factor, which will actually flip the shape around. So it will actually flip shape around. Okay, I'll draw an example, and what I'm going to do is use like ray lines to try and show you what's going on. So if I had a square like this, yeah, and let's say my center of enlargement was here. One way to do it is to count squares or to draw lines through the corners, yeah, and then count the squares, and then I can use that to draw my enlargement like this. Yeah, if it was a fractional scale factor, then my square will probably end up down here looking a bit smaller. If it was a negative scale factor, then what happens is we carry on these lines, so they go through the center of enlargement, come out the other side, and you end up with a shape sort of down here, something like that. Okay, so this one is a positive scale factor, this one is a fraction scale factor, and this one is a negative scale factor. So that's everything you need to know about enlargement. So we've gone through this bit here. We've also gone through this here. Combining transformations is basically doing one followed by the other. So we've got some other stuff here: plans and elevations, congruent shapes, and loci and constructions. Right, so let's move on to plans and elevations. Very easy. So what's a plan? Plans and elevations. Right, very easy. A plan is a view from above. Plan equals view from above. View from above. Now these things are always done 2D, so it's like a flat image from above. And an elevation is a view from either front so in which case it'd be a front elevation or side, or from the side, so in which case it'd be a side elevation. Again, this is 2D, so it's like a flat shape to show what the front or the side looks like. You need to be able to get a shape, work out what its plan and elevation is, and from the plan and elevation work out what the 3D shape that it is and be able to sketch it. Okay, so that means that we've now done this here on this section like that. Okay, so let's look at congruent triangles. Congruent triangles. The word congruent actually means agree. So triangles that agree. So triangles which are the same shape and size. Shape and size. And the way that we can determine if triangles are the same shape or side is by looking to see if they have two angles and a side the same, in which case we use the abbreviation ASA, or whether they have two sides and one angle the same, and they must be in the same positions, in which case we use the abbreviation SAS. We need to see whether they have all three sides the same, in both triangles, in which case we use the abbreviation SSS, or whether they have a right angle. So these to do with right angle triangles. So the right angle, they've both got a right angle. The hypotenuse, which is one of the sides in the triangle, is the same in both, and one of the other sides is the same. Not sides, but just side. In which case we use the abbreviation RHS, and we can use this to help us decide if two triangles are congruent. So for example, here's a triangle, and they're never really drawn to scale or anything like that. Let's say that this is 5 centimeters, this is 5 centimeters, this is 60 degrees, this is 60 degrees, this side is 4 centimeters, and this side is 4 centimeters. So are these congruent, these triangles congruent? Well, let's have a look at the positions. Both of them have a 5 and a 60 next to the 5, touching the 5. Yeah, so that agrees. And also the 4 centimeter is opposite the 60. The 4 centimeters opposite the 60. So these two are congruent because they're in the right position. So we would use the abbreviation SAS. They've got a side, an angle, and a side the same in the correct positions. Now, if I was just to move that 4 and put it somewhere else, if I put that 4 here, these are no longer congruent. Look at the positions of the sides. This 4 is now touching the 60. It's not touching the 60 over here. So just by moving that side, it would mean they're not congruent. So I'm just going to move that back and make them congruent again. So now we've done, or we've proved, we show that we can prove that two triangles are congruent. So we've done this bit here at the top. We've done the enlargement. Combinations, well, that's just doing more than one large enlargement together. So now we've got a few others at the bottom to finish off. Right, okay, so constructions is the next bit. That is different types of bisectors, constructions, and this is linked to loci as well. Okay, I'm going to put links to where you can see animations of the constructions. I'll put those in the descriptions. So the constructions we have are perpendicular bisector. Okay, now what does that look like? So let's say we've got 2 points here, A and B, and I want to construct the perpendicular bisector. I'm not going to show you the method, I'm just going to show you what it looks like. So we would actually draw a line between them and then use compasses to draw a line like this. So this blue line here is the perpendicular bisector, and what's important about that blue line is it's the same distance away from A and B. It's what we call equidistant from A and B. Okay, so this blue line, it's the same distance, so it's always the same distance from points A and B, points A and B. So always the same distance. We use the phrase equidistant, equidistant. So if you see equidistant, that's what it means. And actually another way of describing it is it's the loci or locus. Now the word locus, loci, just means path or route, so path. So it's the locus of all the points equidistant. There's that word again, equidistant. So I just realised I spelled the other equidistant wrong. Equidistant, no I didn't. Equidistant from A and B. So this is linked into this loci. So it's normally things which are always the same distance away from certain points. The other type of, well actually let's finish this off. Perpendicular bisectors. We need to do basically one that goes through a point on a line, through a point above or below a line, and also perpendicular bisector of 2 points. Yeah, and there will be links in the description on how to do those. So that's the first type. The other type of bisectors we need to do are angle bisectors. Okay, so this is splitting an angle in half. So maybe we'll have 2 lines like this. Yeah, and what we're going to do is we'll use a compass to split those angles in the middle without using a protractor. Now, if this at the end here is the point A, and this is B, and this is C, that red line is equidistant from points, or not points but lines, AC and AB. So it's actually halfway between those 2 lines, always the same distance away. So we can call this, another way of saying it is it's the locus of points equidistant from lines AB and AC. So we use the word locus here, this path. So angle bisectors. Now the other types of constructions you need to do, I think the only other one is to construct 60 degrees. So you need to be able to construct a 60-degree angle using a compass. I think that's 5 in all. So now we've done this, angle and line bisectors, certain angles without protractor. Okay, yeah, so we're going to be able to do 90 degrees because that's perpendicular bisector. You can see that in the first diagram, and 60 degrees. And also we've gone through what is meant by a locus. It's a path, and use a locus to solve problems. So here's one example. Here's a line like this. Say I wanted to draw the locus of all the points which were a fixed distance away, let's say 1 centimeter away from that line. Now what that's going to look like is something like this. So I'd have a line around the top which is 1 centimeter away, a line around the bottom which is 1 centimeter away, and then what would happen is we would get this round the ends. Now the reason why we get that is because the locus of a point, a single point, is a circle, all the points which are the same distance away from a certain point. So if I wanted to find all the points which are 1 centimeter away from that, it will be a circle going around there, which is always 1 centimeter away, and I'd use my compass to do that. Yeah, so now we've got different types of locus. When you've got more than one, you call them loci. So singular is locus, like cactus and cacti. Plural is going to be loci. So this just about covers all the stuff in chapter 7 of the Higher GCSE textbook.